All right, so today we're going to finish up the last bit on the technical part of speeding up model predictive control. So last time we talked about this method, model predictive control. It's very nice because it allows us to integrate this optimization-based approach, right? With the fact that this isn't our stochastic, it might, so therefore might not evolve exactly as you expect. And so we can account for all that. Now, the problem with this, though, is that unfortunately what we need to do this well is to solve an optimization problem, potentially a very big one, at every single time. And I mentioned actually in the previous slide here that for this task that I set up here, which is this generator control task, right, where you want to regulate all these around some desired voltage angle. For that task, solving the MPC, as I set it up in the previous slides, takes about, even with very, very fast methods, so this is really me trying to do as fast as I can, without maybe writing my own custom solver, but using Cplex, which is a pretty fast solver, and writing it in a form that's sort of native to Cplex, I can solve it in about 1/4 of a second. And this is actually impressive, right, because there's something like 10,000 variables, 10,000 time steps here, 10 variables per time step, so we have 100,000 variables. This is a, actually, is that right, or was it? No, sorry, 1,000 variables, because the delta t is 0.1 seconds. We have 10 seconds, so 1,000 variables still, but 10 state variables per time step, so it's 10,000 variables. Then you also, for the states, then you also have controls. That's 5,000 more variables. This is on the order of you have constraints and all these things. This is in the order of 15,000 variables here we're solving, and we're doing it in 1/4 of a second, which is pretty nice, but still not quite at the speed that we would want to be able to do it in real time, because the system evolves at, in this case, in the discrete time case, about every 0.01 seconds. So the question is, what do we do? How can we actually apply methods like this in scenarios where things are going really fast? And again, this is a pretty small system. This is a 5-generator system. This is not like the actual power grid. And to some extent, this is just kind of going to be an issue. And all you can do, to some extent, is just say, well, maybe in cases like this, maybe MPC is not quite the right thing. And it probably might not quite be the right thing to do here. I mean, these are sort of very fast control tasks. You might not want to be doing generator scheduling. MPC might make more sense for something like you do on the homework, where you're actually scheduling every hour generation and storage. But when you have a system evolving at the order of 0.01 seconds, that might be sort of not the best application area for it. But maybe you really do want to use it too. So if you do want to use it here, or maybe even if you have a really big system that takes you an hour to solve these optimization problems, you want to make it faster, for like the hourly planning that you're doing on the homework, a big question is, how do you speed this up? Right, because we went from LQR to matrix multiplication in LQR to execute our control to an optimization problem. We need some way of making this a little faster. And as I said before, to some extent, it's just going to be a little slow, right? We are solving complex problems here at every time point. Things may be slow, but we can do a couple things to speed it up some, and it's worth knowing the broad idea about what these things are. So one idea to speed things up is to think about the optimization horizon for model predictive control. Now, I'll go back a few slides here to the actual control task we had, right? So our control task, the thing we're actually trying to solve, is some control task from time t equals 1 to t. Now in reality, t could be very long, right? Because in reality, you probably don't want to control these generators just for 10 seconds. You probably want to control them forever, right? So t here, big T, is potentially very, very long, right? And potentially infinite even. You just want to do this control forever. In MPC, you also have this other horizon, though, which is h. And h is the horizon you use when you actually plan your optimization. Right? You plan your current control. You look h steps ahead in the future. Okay. Now, in this task, I actually, or in this is the first sort of illustration of this task, I actually had these were the same here. So I used the full time horizon at every step. I mean, full, whatever that means. Again, you probably wouldn't want to just think about 10 seconds, but we are here to think about 10 seconds. So I used those whole 10 seconds to plan what I'm going to do, right? But what you can imagine is, well, look, what's going to happen an hour from now, or maybe days from now. An hour might affect things on the level of your planning of renewables, but probably might not affect things on the, the generator control level. But something 3 days ahead from now probably is not going to affect our current actions that much, right? We're trying to control generators, tune up and down the power a little bit. We don't need to really, even if we're going to ultimately use this for 3 days straight, we probably don't need to think about the next 3 days in advance, right? We can think about a much shorter time horizon when we're making those when we're deciding upon our current actions. And so the basic idea here is that this internal time horizon you use to solve your optimization problem, or you use in setting up your optimization problem, can be much shorter than the one you use for actually controlling the system. Okay, so that's sort of speed up number one. We can take this t, which is the actual time horizon of the task, and h, which is the horizon we use for optimization, and we can make this much smaller than that one. So let's see what this looks like. So here is our control. This is what happens in our control problem when we use the horizon, the internal MPC horizon, the same as the actual control horizon, same as t. So it looks pretty good, right? Here, we're going to use the time horizon internally of 2 seconds, so 1/5 the amount of the true control horizon. And I would actually be pretty hard-pressed to tell a difference between these two graphs here, right? It looks pretty much exactly the same. And all that's saying is, in your optimization problem, what happens in the future, assuming everything's evolved according to the linear system, it isn't going to really affect what you do right now that much. There is a limit to this, though, right? If you think too narrowly, and so you don't think far enough ahead, you could take actions that are really sort of just not going to put you in a good situation in the future. So the idea, I think the extreme case would be, suppose you have some penalty on your state and a penalty on your control input. If you just took a time horizon of 1, and I don't mean 1 second, but just 1 time step, and just look at that current time step, right? This is sort of the simplest possible case. It's almost silly, and it is silly. Then it turns out that anything you did with your control wouldn't have any effect on your cost, right? Because you can't actually affect the state at all. You're not going to even think about even the next time step when you're computing your cost. And so you'll just use the minimum possible control, which is basically 0. And you'll just keep doing that. You'll just keep saying 0, 0. That looks good because I can't really do anything. So I'll just keep picking 0 as my control. And while that obviously is an extreme case, that same idea manifests itself when you pick too short a time horizon. So this slide now shows some things that happen when you start going slower. So now I'm going to start picking h of 0.5 seconds. It looks okay. Things might eventually get down to a good state, but it hasn't gotten there after 10 seconds yet. And then in contrast, something like 0.01 seconds, well, now we're actually doing really badly. We don't ever get to where we want to be. We don't ever converge to the desired position. And the reason for that is this, with only a look ahead of 0.1 seconds, you can't really affect the system very much in 0.1 seconds. So the controller is not going to take any action to try to correct things because it thinks, well, the best thing I can do is just leave things as they are, right? Because that's not much control action. I also have a high penalty on my control costs. I'm just going to sort of leave things as they are. And what you see there is that things don't work out very well at all. So that's idea number 1. Idea number 2 is that there's no real reason. I mean, MPC, as I put it before, was the idea is you take you optimize something, you take the first action, then you see what happens, and you optimize again. And there's no real reason you have to do that every single time, right? In fact, our time was somewhat arbitrary, what we picked for our time here, right? I mean, I picked 0.01 was our time, but that's just because I'm discretizing some real-world system. In reality, you don't have to think about solving this every single time, right? The reason why we wanted to use MPC, why we didn't want to just solve it once and execute our actions going forward, is that the stochasticity can build up over time, right? So over time, you will have more error in your system. Things will diverge more from what you thought they were, and so you will do badly. But over a short time, this isn't as much of an issue, right? Because over a short time, probably the noise won't be that much, and so you can just execute exactly what you saw, what was planned for several steps in your control task. And again, the intuition here is that over short time periods, the effects of stochasticity aren't very bad. So instead of resolving our optimization problem every time, we're going to only update it, resolve it every, say, k time steps. And in between those solutions, we just execute the solution from our old problem. Does that make sense to everyone? So what this speed up is? It's different than the last one, where rather than thinking about it for shorter horizon, now we're just sort of letting it go for longer before we resolve. So again, here is some graphs that show you this can work very well. So here is, if we update it every 0.1 seconds, here's what happens. So we're resolving our optimization problem every 0.1 seconds, which just happens to be our integration time step, I guess. Alternatively, let's just solve it every 0.1 seconds. So basically, instead of just taking the first action that we solve here, now we take the first 10 actions we get back from our optimization problem. Right? And again, I'd be hard-pressed to to tell any difference between these two things here. But again, there's a limit to this, and that's the whole point of the multitude control, right? Is that we didn't want to let it go for too long. So if we start updating every 0.5 seconds, it still looks okay, maybe, but it's starting to get a little bit noisier here. And you update every 2 seconds, and then this is clearly a situation similar to what we had when we used this pure optimization approach, and we're not regulating very well. The stochasticity is building up over that time, and it's causing us to perform badly. So these are somewhat tricky things, right? Because they're how short is too short? Well, it completely depends on the dynamics of the task itself. For a problem like scheduling renewable resources like you're doing for the homework, we're even only thinking about a time horizon of 1 hour, or sorry, a time step of 1 hour, right? So things aren't changing very fast in that 1 hour, perhaps. Here, you wouldn't want to go for an hour without updating your generators. So the right horizon, the right amount you can shorten that internal planning horizon for MPC, and the right amount you can sort of go between updates, that's all very problem dependent. And it's going to take just basically some trial and error, or maybe some understanding of the system that you actually care about, to know what settings you want to use for these different things. But putting it all together, we had a system here where maybe we can update it every 0.1 seconds. Maybe we can use a shorter time horizon internally of just 2 seconds. And putting these all together, so on my desktop, if I use internal time horizon of 2 seconds and update only every 0.1 seconds, then the solution to the optimization problem takes about, solving the optimization problem with this horizon takes about 0.08 seconds. We're only updating it every 0.1 second, so now we can do it in real time, right? We've set up a problem framework where our solution is faster than we need to update, and so in fact we can do this. Now you might also say, well, this does take some time, and so when you start solving the problem, you'll have some state, and by the time you actually get the solution, you'll have gotten another one. But we'll ignore that for now, because it is still a case where things are short. I mean, I'm not ignoring it. I'm just saying it still works okay. And the idea is you have the same sort of effect where what you did in the past is still valid. So because it sort of doesn't take too long between different updates, what you planned before is still a good plan, and so you can just go ahead and execute that as you solve new things. So what this boils down to saying is that this is now, for this problem, faster than real time. So we could execute it on a real system controlling these real generators here. Now again, this is control on my desktop, which is a pretty fast machine. You couldn't probably put it in like in a little embedded processor to make it that fast, right? And so there's still some question about whether you really want to do this for a task like this. Maybe you would need to have some sort of LQR controller that worked in the meantime, that kind of stabilized things in the meantime. And you can do all sorts of sort of hybrids between different approaches here to try to get at what you want. But the basic idea is that with these tricks, we can speed up optimization a lot, and a lot of times make tasks like this practical in domains where they otherwise would not be practical. And as I said before, it is true, though, that MPC probably is most often applied to cases where there is significant time between control actions, like hourly planning for renewables, right? Or like maybe 5-minute dispatch of market dispatch, or things like mechanical or industrial processes that change kind of very slowly over time. So it's okay to make an adjustment every 5 minutes or so. Just because we're not quite there yet with really high-speed optimization. And so you probably want, I mean, I guess we actually are, and actually in a lot of cases the practice is not yet caught up to the technology we have. But even 10 years ago, we couldn't solve these things nearly as fast. And so systems that are actually in operation right now typically are those that have longer times between control actions. I should say this is changing. These new technologies are enabling us to use these techniques really in a whole variety of new domains where we could not use them before, but there is still this sort of divide here. Yeah?
What did it mean by faster than real time?
Right, so what I mean is we solved the optimization problem in 0.086 seconds, and we are changing the control input every 0.1 seconds. And what I mean by that, faster than real time, is we are solving the problem faster than we need to update the solution. So on a real-time system, it would work. Basically, we have some time to spare. So if we were simulating it, we could do it faster than real time, right? Because we can just take this time to simulate. Right. So if we could, whenever we can solve it faster than it takes, faster than we want to update the system, I'm calling that faster than real time. And really, you really have to be in that regime to use MPC. Otherwise, on a real system, you wouldn't be able to. All right, so the last thing I'll add here, which is just sort of, again, a little bit, doesn't have much content to it, is that, well, the last thing we can do is just, well, let's just solve our optimization problems faster, right? However we want to do that. And this is sort of one of those things where what's been happening in technology in general is enabling huge new applications for something like MPC. Because I said before, 10 years ago, we couldn't come close to solving these problems this fast. So what we're going to do, right? There's a lot of work on, actually, before I mention that, I should say that, so fast optimization is a big win here. And for something like MPC, as mentioned before, using solvers that take as input a standard form problem, so just plugging in a standard form linear program or standard form quadratic program into something like CPlex is typically going to be a lot faster than using YAML, because YAML has to run a lot of MATLAB code to parse these problems into standard form. That's what it's doing behind the scenes, right? So if you want to build a fast MPC algorithm, and this is in fact what the 830 class is doing on the homework, you have to implement these kind of solvers, or you're going to want to implement them in standard form, not as a YAML program. And that's probably still true. Maybe eventually we get to the point where these type of solvers can go really fast, but we're probably not quite there yet. There's also been a lot of work on speeding up optimization kind of in clever internal ways. So remember, the idea of MPC is that we're solving these sort of long tasks one after the other. right? So we still typically have a time horizon that we optimize over that's much longer than the time between updates, right? So at time t, we solve some set of control inputs there. Then we move forward a little bit, and we solve some new set of control inputs that might have changed from that since, and I guess it goes longer, since we are not quite in the state that we thought we were in. But the idea is we can still use this partial solution as an initialization point for the new solution. So not all methods, but some methods, for example, some linear programming methods, can work a lot faster if you give the solver, like Cplex, a good initial guess. And these old solutions can serve as very good initial guesses for the next solution. Right? So we can oftentimes speed these things up a lot just by being more intelligent in how we sort of initialize our optimization solver. And then finally, there's some if people are interested in this, let me know. There's some very cool recent work on basically building very small, very fast custom solvers. And the idea here is that when you solve an MPC task, what you're doing is you're actually solving a very similar optimization problem again and again and again, right? Most of the structure of the problem does not change. All that changes is maybe a couple of the inputs, a couple of the constraints, is all that change between iterations. So you can actually take these general solvers and figure out the precise trace that they go through in their solution for your type of task, right? And you can essentially generate code that has, for example, almost no branching. It just is a big code of a huge execution file of runs operations in this order, and then we know we're going to converge. You can actually write code that will be specialized for your particular problem instance. So there are some software packages, and they're fairly new. This is sort of a very new direction. But you can sometimes make specialized, and not like write them from scratch, but basically use a code generator that will generate specialized solvers for your problems. And that can speed up things like MPC a lot. Okay, so this is all I'm going to say about speeding up MPC. Again, this is sort of a, this is getting to be fairly advanced topics, right? And there's a lot of current research going on about how you solve things like MPC faster, how you can speed up optimization. And there's some really amazing recent results on how much you can speed up these things and how complex of systems you can control using this kind of online optimization approaches. So this is some brief issues here, but the basic idea is that we are solving complex problems, and you want to try to speed these up as much as you can to solve them well. Yeah?
For the last solution, would they be just taking the YAML or C-type code and...
Yeah, they would essentially be taking a YAML type code input, or they could take like a standard form. Either way, really. They could take a standard form problem and convert it into customized code, or they could take even a YAML type description. So you actually could write it in a language like YAML and get as output a customized solver. Both of these will work, or there exist both of these. Okay, so before I move on to the very last thing, the last couple lectures, which are just sort of about some future directions in research, I wanted to mention one aside, which was about learning dynamical systems. So the assumption throughout our unit here on control was that if you have a system like xt plus 1 equals ax plus bu, we assume that a and b are known, and we know them beforehand, right? But we've always assumed those things are known. For LQR, they have to be known. Maybe for PID control, you could sort of not have them known, but then you have to pick the gains, so you have to pick something anyway. So we've assumed these things are known, say by physical properties or something. But the reality is, a lot of times you won't know the model beforehand, right? You just have some data, and you won't know what model generated that data. And here, these methods don't at least seem to be immediately applicable. So typically what you do in a situation like this is you switch between a learning phase, right, where you're going to learn these models, and then a control phase where you're actually going to control the system based on your learned models. The basic idea is, if you observe some, even if we don't know A and B, if we observe some sequence of control states and control pairs, like they're not just pairs, but a whole sequence of state, input, next state, input, next state, etc., we can use machine learning to learn these models, right? So in a little bit more detail, suppose we have this collection here. X, Y, and then I should mention, this is sort of an aside. You're actually doing this on your homework. You're learning a linear dynamical system, which is an autoregressive model. So you are already doing this. But more broadly, I think it sort of is good to know, at least this can be done in the general case. Suppose you have some sequence of things here, right? Well, what the function you want to know is some mapping from from current state and current input to next state. And what you have is you have a bunch of examples of those type of pairs, right? So this looks very much like a machine learning problem, right? Where what we have is we want to learn some function xt plus 1 equals f xt ut. And again, apologies for this notation here because each domain has its own notation, but you can basically think of this like your desired output, yt, and this as your desired input, xt. Again, with apologies for the fact that these are the machine learning inputs and these are the actual control type notation here that I'm mixing. And machine learning, again, was really good at just coming up with mappings from input to output. What we have here is we have a bunch of input-output pairs that we've observed. So we can learn a function that will actually predict for new states and controls what's our output, what's our next state going to be. And that is just a machine learning prediction then. So in the simplest case, let's just learn a linear model. If we start doing nonlinear models, then we have nonlinear control tasks, which get a lot harder. So let's think about learning a linear model. And the idea here is that for, say, least squares, you would just want to find the A and B that solve this optimization problem. You have some sequence of t observations you've made, and you want to minimize over a single A and B. What is that single A and B that for all these things minimize the sum of all these errors here? All right, and though it's maybe not immediately obvious, this is just a least squares problem. This element here is the outputs. In fact, it's actually, there's going to be n different least squares problems because you have n different outputs here. And each least squares problem would correspond to one row or column, one row, I guess, in A. But it's just a least squares problem. You can formulate this as A equals V transpose V inverse V transpose X, where X is really a sort of a concatenation between these two things. Now, the way you do that is, it's a couple lines of math, but it's very simple to convert from this to a least squares problem in the form that you saw. Again, actually n different ones, because in normal least squares, this is just a squared term here, because there's only one element you're predicting. Here you're predicting n of them, but that's just n different least squares problems, right? Now, there's one sort of very subtle issue here, which I won't talk about at all, but I do want to highlight for people that might see this come up in later work. If the system really is linear, maybe say linear with Gaussian noise, then this works really well. And you will, in fact, find, or in the limit, find the true A and B that are your system. Right? If they really are linear, those will be a solution that have 0 error. And everything, I say everything's deterministic, and they really are linear. The true A and B will have 0 error, and so you will find those. The problem is when this is not quite linear, which is almost always the real world, is situations that aren't quite linear. And then you have this interesting issue that comes up. Because then you can still solve this, and you might get a good approximation to A and B. Right? Maybe it's almost linear, but not quite. You can still just solve this and get a good approximation to A and B. The problem is that approximation is going to depend on the precise data you've seen, right? Because we're trying to minimize our error over data we've seen. And so the way you generate this data actually affects your solution. So I'm just saying we have some observed sequence here. Presumably you have to get that sequence somehow, say by running a controller, maybe a simple controller that you come up with first. And then the question is, there's going to be some error, and the states you actually care about in some sense aren't these states, right? Because these states are going to be potentially very different from the states you actually want to control your system to. This is a hard problem. And there are many solutions. There's no single one obvious solution. But I just wanted to mention that because we're not going to talk about it any more than this. I'm going to switch to the next set of lectures now. But it is simple in some sense, learning a model. It's just least squares, say. That's simple. But there's a lot of complexities involved, especially when systems are not actually linear. A lot of kind of subtle issues that may come up. Okay, so this concludes sort of the technical portion of the class. The rest of the 2 lectures I'm going to spend, oops, I erased it. The rest of the lectures I'm going to spend talking about kind of in vague terms, and these next 2 lectures by all means sort of interrupt and ask questions and let me know if you have certain areas you find interesting or not. Because they're really just meant to highlight some future directions in current directions in research, future directions that are interesting to explore, etc. But before I go to that, is there any questions about this or really about anything related to control? Because we have now finished our unit on control, and we are moving on to the conclusion. Yeah?
What are some common other loss functions?
Right, so you, and this kind of relates to this issue here, right here, where you might want to use, if you have a bad distribution, you might not want to use the least squares function. So things like absolute loss would be another natural example for what you might want to use there. There are things that kind of meld between absolute and squared loss for regression problems that are like squared loss in some areas, but like absolute loss in other areas. The way this can have a big impact is in the situation where you don't really have the right set of states. I mean, so if first of all, if this can be made to be exact, then all loss functions will be 0, right? Because these are always, this term here is always equal to that, and so any loss function is going to be 0, so probably any loss function will work. Where it gets tricky when there's some subtleties involved is when you can't get 0 loss here. And maybe you don't quite have the right distribution, or things aren't quite linear, and you want to learn a certain A or B that's good in some regions of the state space. And for that, you do have to really think about what loss functions you might want to use. Despite this, squared loss is still very common, I should add, but you might think about different things. There's also some interesting work on using loss functions that minimize error not just over one prediction, but over multiple predictions. So say you make use your initial state and then a fixed sequence of controls to predict k steps ahead. Can you make a loss function that captures those k step errors? That actually ends up not being a convex problem anymore because you have things like a to the k terms in there, and you're minimizing over a and b, so that's not allowable anymore. You can't do that easily. But there are some interesting things you can do in those domains. Okay. So that is the end of that bit, this class, and almost the end of the whole class, I suppose. But all I want to end with, get this up, is some work on some future, I'd probably call something like some future directions in sustainable energy, because this is by no means an exhaustive list. But the topics in this class, we've covered in this class, lay the groundwork for a huge amount of ongoing and current research in this area. And there are a huge number of directions, and you can sort of see these just by, for example, looking at some recent journal publications. These type of methods are used all over the place to address issues in sustainable energy. Now, a lot of them are actually, I mean, machine learning and control, these methods we talked about, are actually finding application in a huge number of domains. The power system stuff was obviously kind of specific to energy systems. But these topics we've covered really are at the forefront of a lot of research in these areas. And if you read some papers in these areas now, you should be able to actually put it into context about what we've been doing thus far. Again, sometimes it'll be a little hard to read some papers because they can be kind of complex, notation can be hard, and they might not quite map the things directly. But the ideas oftentimes build on the kind of stuff you've seen already in this class. And so I think a large number of current research papers in this area you could actually read and understand pretty well, at least the broad ideas. So there are, of course, a huge number of possible research areas and directions for future research. And I want to highlight just a few of these, ones that I'm excited about, that I see a lot of interest in the community, and which really can be put into a very nice framework of building upon, certainly, but using the tools that we've talked about in this class. And the 5 that I sort of picked to mention are renewable integration, and I'll describe all these in detail. This is how you account for the fact that there are a growing number of resources that we can't actually control delivering power to us. There's issues of grid security and resilience, and both in terms of cybersecurity, protecting against malicious cyber attacks, or just in sort of more systems type security. We want to be fault tolerant and don't want to have the whole grid go down every time there's a generator that goes down. There's a lot of work in smart homes, and I actually do a lot of work in this area on a specific topic called energy disaggregation, or also called non-intrusive load monitoring. Since I work in that, I'll actually take a little bit of time and mention some of the stuff that we're doing in that area, and kind of, I think I covered it a little bit when we talked about classifying different types of events in a home, what those different types of appliances are. But there are more advanced techniques that really sort of do much more of a kind of source separation view on this. We're actually trying to separate out different sources that contribute to the whole home energy signal, not just identify individual appliances. And then also some work in demand response and then microgrids. And I'll get to some amount of these 3 today and then cover a little bit of these 2 next Thursday. I should mention, though, that there are a huge number of other areas that are of interest. This is all kind of focusing on computational areas or aspects that have computation to them. There's also a lot of work on just kind of more, more traditional power engineering and power electronics and electrical power systems work. That's more just about building a really big moving generators, basically, right? Building big spinning systems or big high-speed switching systems. And they, a reasonable source for a lot of these things, at least to see the variability of what's going on, is this new journal called IEEE Transactions on Smart Grid. It's still a growing field. I think this journal started it was 2010, I believe. This is a really, really new journal. It's still trying to sort of find its right scope and its right area. I would not recommend kind of reading every article in that journal, that you might kind of go crazy. But you can take a look at least at the titles, maybe the abstract, to see what kind of things are being done. And what you'll find is that a huge amount of these techniques are being employed. So let's just go through some of these things, and this is all very informal. I please ask questions. I mean, you can ask questions for everything, obviously, but in this in particular, if you've heard a different take on a method like this, or if you sort of have seen different ways of approaching this, ask me about it. If you have questions on a certain area, ask me about it. The idea here is really just to show that these techniques do build a foundation for what is going on in the research, and hopefully to spur some interest in particular areas that might be exciting for people. Okay, so let's talk about renewable integration. And in fact, we don't talk about this too much because you're already doing this on your homework, or you're doing something very much like this on your homework. The challenge, well, I guess this isn't quite the challenge, but this is a fact, I guess, is that a lot of states have passed, not Pennsylvania, I should add, but a lot of other states, we are sort of, gas and coal country here, I guess, but a lot of other states have passed pretty ambitious legislation requiring a certain amount of energy in the state come from renewable sources. And I think one of the prime examples here is California, which by 2020, so that's not that far ahead, right? We got about 7 years to do this. They want 33% of their energy, a third of their energy electricity, to come from renewable sources. I should probably mention electricity here, not energy, because it's certainly, we're still driving and heating homes with gas, but 33% of our electricity, their electricity, should come from renewable sources, and that's mainly wind, solar, geothermal, stuff like that too. I believe hydro counts for that too. There aren't that many more dams to build, but there is a good portion of the country's power that does come from hydraulic power, so we should keep using that. But this is still a pretty sizable chunk here, and a sizable new chunk we have to add. And the problem is that, it's what you've seen in this homework, right, is that you can't, unlike traditional generation, where the ISO, PJM in our case, right, could tell everyone, here's your bids for electricity, here's your cost functions, here are the demands we're going to have, or predictions of demands we're going to have. I'm going to schedule the power to be like this, you generate this much, etc., and that's sort of just what happens. All of a sudden, you have these generators that you can't tell them what to do. Right? This is the problem you're actually dealing with in your homework, right? Because you have this wind power that is just going to be what it is. What do? You can't tell it, oh, only generate, or now step up your wind power to generate 5 megawatts of power. It's just the wind's going to blow as it does. And same for solar, right? You're never going to get solar at night, for one thing, which is okay because we actually use a lot less power in the night, too. But there are clouds and stuff like that, right? You can't tell it, okay, don't get cloudy right now. And this, in the current grid at least, this is sort of mitigated by the fact that there aren't that much of these things, right? So it's sort of okay that we have some wind blowing, because if we have some wind blowing, we'll just turn off one of our generators or a couple of our generators. And then we'll maybe use these generators that can ramp up and down very fast. This is talking about those open cycle gas turbines that we're talking about in the homework. And some generators can sort of step up things up and down very quickly. And so you just say, well, those guys that can move quickly, they just sort of follow the wind. And if it's blowing, they don't generate much. And if the wind's blowing or not blowing, then you generate a lot more. But when you start getting to 33%, a whole third of your energy from wind, this gets trickier. And these problems get a lot bigger. And you need to do this in kind of the classical sense, without any storage, for example. You need a whole lot of these generators just kind of standing by idly, waiting for the wind, to see what the wind does to decide what to do. And when they're standing idly, by the way, they're not really idle. They're spinning a little bit, some of them. And so we are actually wasting power. So how do you deal with all this, right? And a huge way of dealing with it, right, is just better predictions. I mean, if you can predict things better, you can do a better job at these things. So I want to show a few figures here. This is from this is ISO New England, which is the PJM equivalent in New England. Did a couple years ago, a study on wind integration in New England. And they sort of said, okay, for different levels of penetration of wind, right now there's So I think this is much more. Or no, actually, it could be total penetration here, actually. So what this is saying is that this is how much more wind we add to New England. All the partial Q means here is these are sort of in the queue. They're going to be built anyway. So we're sort of building some of what we're going to build. These are ones that are like all the ones that are currently planned. We're going to build all of those. Build some more, build them offshore, onshore, see what happens. And for these different scenarios of how much wind, and this is just 20% wind at the maximum. So this is probably, with 33% renewables, maybe you'd have 20% wind with sort of a nice mix of other things too. In New England, you probably would, actually I'm not quite sure what there's a lot of hydro there you can get from like the Niagara Falls and stuff, but there's I'm not sure how much solar. It's probably not the best place for solar in New England. So what this study showed, though, was that for different amounts of added wind power, how much more regulation, and there's two types of sort of added power. There's what I'm going to show here is one slide for regulation and one slide for reserve. Regulation is kind of like the super, very, very fast response. This is things that can come in within 4 seconds. It can start bringing stuff up and down. And then reserve is more like 10 minutes. You can bring something up and down. So this is how much more regulation you need, which is very, very fast response, very expensive, and actually kind of very, typically very carbon wasteful, because they have to have these things that are maybe spinning always or maybe kind of almost ready to start spinning, et cetera, that are less efficient than the ones that generate a baseline load. And so for increasing 20% wind, we have to really increase our total regulation by a huge amount here. In the current scenario, it's about 82 megawatts of regulation New England has. We have to raise this to 290 when we have 20% wind. And the reason is that wind is going to blow, and we need the ability to track very, very short-term peaks and valleys in that wind power. We need to basically be able to stabilize it with all this extra power that we have. So again, what do we do here? I just mention that if you download these slides, all these links here that are in blue, those are links to the actual papers. Some of them you have to be on CMU campus, I believe, to download. They're like links to IEEE Explore that you have to have a license for. Some of them are just, when I got just the actual link from someone's webpage, but not always that exist. We can show a similar chart then also for just the reserves, which are, as I said, similar regulation, but just operating more like the 10-minute scale. So this is kind of just power that we have ready to go. Either can be spinning reserve or non-spinning reserve. Spinning reserve means there's actually, these generators are actually spinning. They're just not hooked up to the grid. And non-spinning reserve means they will need to start spinning before we hook them up. And again, you need a pretty big increase to get things to work. We already have New England already has a fair amount of reserve already. It has about 22,000 megawatts of reserve. But we still have a pretty sizable increase on that if we want to go 20% wind integration. And just to put it in perspective, I guess these numbers don't really mean all that much. But for example, today, the maximum forecasted load was 17 gigawatts of power, 17.5 gigawatts of power. So these are actually pretty sizable portions of the total load in New England that you have to add. I mean, not as much as 20%, but maybe 5%, right? That you're adding just to keep up with this 20%. Meanwhile, these generators are standing idle most of the time, right? So is the company going to want to build a generator that can't, rather I should put this as what's the right sort of incentive structure and pricing structure to have so that people will want to build generators even if they stand idle most of the time. And so how you develop the power markets to allow for this is a very important question. The other really important question, of course, is how can we do better? If we know what was going to happen with the wind, we could probably do a lot better than this, right? Because we wouldn't have to have things that could respond quite as fast. We could kind of make better plans ahead for, the wind's going to drop down in 20 minutes, get some things that may take longer to speed up, get them going now. So predictions really factor in very heavily to these numbers. And in fact, if you want to know how they come up with these estimates, what they did was actually very similar to what you're doing on the homework. I mean, it's sort of a larger scale thing, and they're using more data, certainly, but it's very similar. They're running a bunch of scenarios. They're looking at those two types of plants, right? Those fast open cycle gas turbines that can turn on and off very quickly. That's generator 2 in your example. And the slower ones that sort of have to, can't react very quickly. They're seeing how much more of those fast ones we need if there's a certain amount of wind. And as you raise the amount of wind power, you will find that you need more and more of those types of fast-acting generators. Now, that is mitigated by the fact that if you have storage, you can account for some of that, right? Because if you have storage, if we had infinite storage, this would all be kind of easy, right? We could just take the power, store it as energy, rate goes in, we build up energy in our batteries, and then when there's no wind, we just take out of the batteries. We don't have storage anywhere on that scale right now, so the way we go about solving all these things is some combination between intelligent planning, right market structures for these things, some amount of storage, and prediction, right? Doing the best we can to predict what's going on. And all those things coming together is really how renewable integration is going to be dealt with. And so all the issues we covered in this class, really, from optimal power flow to prediction to control, those all factor in to how we do renewable integration. I should also add, these papers are going to be harder to read given the background of this class. Most of the papers should be sort of intuitive, the ones that I'm going to point you to, but these ones are pretty tough. There is another line of work that's a little bit different from this. So we've been taking kind of this model predictive control type approach, which is essentially saying, okay, I'm going to make predictions, going to optimize based on that, but it's not an optimal approach, right? That's sort of the first thing I said was this is not the actual optimal strategy, it's something that works well in practice. In the general case, general stochastic optimal control is very hard. So a parallel line of work has been focusing on, let's look at cases, there might be simplifications, but let's look at cases where we actually can solve that stochastic optimal control problem exactly. And some of these papers, which again, these are just two examples. These are not necessarily, I'm not advocating these as the best approaches, certainly. But these are two examples of analyses where people take a simplified version of some of these control tasks, though still quite complex in a lot of ways. Think about particular stochastic evolution, like particular distributions for how systems evolve. And they come up with analytical solutions to, say, optimal control of renewables or things like that. Dispatch I'm using as just a sort of way of integrating renewables and dispatching power to account for renewables. These come up with optimal strategies for handling these specialized cases. And there's oftentimes a lot of very interesting kind of structure in what the optimal solution is, right? So for example, sometimes for energy storage, a very simple policy ends up being optimal. Which kind of makes sense, right? Because, I mean, you can imagine a lot of cases where something like, if the wind's above a certain threshold, then charge your battery. If it's below a certain threshold, then put out power from your battery, right? That's a pretty simple strategy. Not close to optimal in the general case, but there are cases where it is optimal. And so figuring those cases out and understanding when certain things actually are the best thing to do, both lets us kind of analyze what happens in more concrete numerical terms and helps us understand when those simple strategies are in fact optimal. So I sort of see this two different kind of parallel tracks for how people are dealing with renewable integration. On the one side, there's people doing kind of the more practical, run simulations, build complex models, do lots of prediction. On the other hand, there are still complex models and predictions here, but on the other hand, there's typically sort of, and then what you get out of these things is you get out sort of a lot of numbers, and you just average them, and you maybe get some empirical result. What you get out of here is more sort of proofs that under certain circumstances, certain actions and certain policies will in fact be the best ones you can possibly have. And these are both really interesting lines of work on how to approach problems like this. Yep. And in fact, we saw cases of this where we could do something like this, right? In the cases of, say, linear models, if everything was linear with no constraints, then we apply things like LQR, right? That's optimal there. We saw things like MDPs, where we knew how to solve an MDP optimally. So these are more complex than that, but that kind of gives you some insight. And there are some limited cases where we can solve them, And it's worth thinking about those cases to a certain extent, in conjunction with the more broad simulations as well. So that's all I'm going to say for, I'm not actually going to give much sort of concrete examples or any sort of show plots for renewable integration, mainly because you're actually going to do those on the homework yourself, right? So you're already doing this. You're running simulations of what happens under different amounts of wind being present, different amounts of different costs for generators, different allowable ramp rates. These are all very complex things. These are exactly what they do in renewable integration studies, and you're going to be generating those results on the homework. So we'll leave it at that for the slides here. Yeah.
Seems a little for the reserves or the ones before.
Yep. These ones.
Yeah. So as more wind comes on, won't they just take a fixed percentage that you'll have to add this amount of reserve just to keep it from?
So it can actually be complex because what it depends on also is how correlated the wind is with other wind farms, right? So if all wind came on or went off, then yes, you would need a fixed percentage. If wind was either full on or full off. But if you add lots of wind in different places around the state, you might benefit a little bit from the fact that, if it's not blowing here, maybe it's blowing somewhere else. Unfortunately, you can't exploit that fully because lots of times the wind actually is very correlated, right? So if it's a windy day in Boston, it's probably going to be a windy day, and it might be a windy day in New Hampshire too. So there are extents to which you can get around this by scale of a deployment, but it's actually all very complex to do. And really the only way to really, and this is actually why it's good to do these kind of studies in conjunction with the theoretical analysis, is because a lot of these things are very hard to analyze theoretically, right? When you have these very high dimensional correlations, very hard to model distributions here, how do you know sort of what the right thing to do is? And things like MPC give you, with some modifications I guess, but things like these give you ways of thinking about how to handle certain scenarios. And those scenarios, if you run enough different scenarios, you can start to get some idea of what the averages might be like. And so if you build your sort of wind modeler from enough real data and you trust it enough, then when you run everything together, you will get a good estimate of what you really need in addition to that. With the caveat that this is all simulation to a certain extent, so this is sort of our best guess. The thing to do is usually make these kind of conservative so that you will hopefully not get yourself in too much trouble here. Basically, be pretty sure that you couldn't possibly need more than that, but you might actually need less.
They're ultimately still based on these models.
Yeah, so these are all based on models. They're based on simulations. They're based on model predictive control. They're based on forecasting of wind. They're based on the actual observed history of wind. They're based on all of this. Okay, so maybe the last thing I'll talk about today is grid security and resilience, I'm calling it. And in the context of the smart grid, when you hear the term security, it can actually mean two different things. Right? It can mean either cybersecurity, which is essentially how do we protect grid resources from cyber attacks, from people hacking into systems, manipulating them somehow, and messing up the system because of that. There's also reasons you might want to do this. You might just be a malicious person. That's not a person, but you might be trying to attack the system and trying to bring down the system. You might be just trying to get free power, right? And so you maybe can just hack into your smart meter so it doesn't report any data to the utility, and so that you don't have to pay any power bill. Those are probably covering the spectrum of things, or you might just have a situation where there's some malfunction in a computer somewhere on the grid, and this causes some bad measurements, and this causes the system to have some big issues. So all these things fall under the broad kind of scope of cybersecurity, essentially. I guess the last one is sort of errors, so it's not quite cybersecurity. It's more sort of malicious attacks is the domain of cybersecurity. And the other thing people mean when they say security is actual resilience to actions like physical outages, right? So if a power plant goes down, can you recover from that, or do you have a big blackout? That's also goes to the name of security. The transmission line goes down. Is that going to destroy your whole system, or are you okay with that? And so this paper, for example, here, and like I said, all these papers, if you just click on the link in the PDF, you can see the paper. This paper calls it real-time dynamic security, but it's really talking about outage prevention. So all these things, people refer to them as security. You can usually tell which one it is just reading the abstract of the paper. You'll figure out which one it is they're talking about. I should mention, these more and more are coming together, right? So more and more you have problems where there's maybe a cyber component to an attack, but they're also attacking physical properties of the system. So you're using a cyber attack to bring down a generator in a way that can bring down the grid afterwards. I mean, this is if you are a malicious person trying to do this, right? And I guess the buzzword people use to describe these things are called cyber-physical systems. So these are systems that have some sort of physical element that operates according to certain physical laws, i.e. the grid and generators, and then the cyber element, which is a networked infrastructure connected somehow to a network. And these things bring together these two types of issues, and more this can become a problem in grid systems, right? I'm going to talk about just this one. The cybersecurity element, there's a lot of just normal cybersecurity issues that come up, as in any cybersecurity class that you would take. The sort of the interface between these two things is where it gets interesting. But I'm going to talk about just kind of the old style of security here, which is just resilience to things going down and bad things happening in your grid. So let's talk about, I'm actually going to, and this paper talks about something similar to this. It's a little bit more, they don't talk about it in as much detail, but they also are using a much more complex model. But let's just connect this to what we've seen so far in the class. Let's go back to our favorite, which you're probably sick of at this point, our favorite linear dynamical system, where we're talking about a generator evolving according to these laws, right, where we have laws of a generator and then our power flow model. Everyone remembers this? Because I kind of almost beat it to death, so hopefully that rings a bell. And let's talk about a little bit different setting that we had before. Let's talk about just frequency regulation. So before I was talking about in our system, we wanted to get the voltage angles to some desired quantities, right? We wanted to make them some desired numbers because that would make power flow the correct way, essentially. The reality is this was a good example for the class because it highlights the second order nature of a system. And systems have both data terms and their derivatives in it. And a lot of control is sort of thinking about second order systems like this. But a more common paradigm in some sense in the grid is actually frequency regulation, where you don't really care about their angles. What you really care about is just making sure that every generator and every node has the right frequency of the grid, right? I mean, maybe you probably have some constraints too on, say, how much you can transmit over a line, but you don't always want to say, I really want to be at this precise power angle for my generator. You often would say, no, I want it to be on at a certain frequency. I just want to make sure it's operating at the right frequency. And it's also easier to do this in some sense, right? Because power angles, those really only make sense relative to each other. So in order to know your power angle, you have to kind of synchronize to some global source. Whereas frequency, you can measure just at the source. So a common way of doing this would be, I'm calling it PI control here, but really you can think of it as like DI control, because this term is a derivative term. So it's OK to apply P control on this one. There won't be those oscillations you had for the general case. And basically what you do is you just apply a PI controller at each generator to get this to be its desired value. And as long as generators can sort of produce more or less power, depending on where they happen to be in the network, and they have some flexibility there, that works okay. As I said before, in the real situation, you might have some generators that do this, and other ones just produce a fixed amount of power, and then some others that kind of regulate frequency. But we'll assume that for now they're all regulating the frequency or working to regulate frequency. So we have some sort of just simple control law where we just say each control input's just going to be, it's going to look at its current frequency, going to look at where it wants to be, and then multiply that by some constant, some gain term there. And also we're going to add up the errors as we go to have that integrator term. We're also going to have a term that depends on the integrator. So kind of going through this quickly, but basically this is just a control just to keep frequency at desired amount. And if we take our scenario, so I guess it was the 14-bus system with 5 generators that I was using before, and so we're going to use that same one again. And see what happens. This works. I mean, I picked some gains. They didn't take too long to find gains that worked here. Each generator just says, okay, I'm going to look at my frequency. I'm going to act based on that, and then see what happens. Right? So it goes along and it maintains, and it is with noise too. So the reason why this isn't exactly 0 is because there's noise in the system. But it, loads change, it changes. This is very, very nice regulation. There's nowhere close to, I think, this amount of regulation in the real grid. But this is in degrees, or sorry, radians per second. So this is very, very good regulation here. And we would do it forever if you had this amount of noise in the system. Now, let's say, and this is for 100 seconds, I'm showing this for. Let's say now at time 100, we have an outage at 2 of the generators in our system. And all of a sudden, they start producing 0 power. Everyone else just keeps acting as they would before. And so you might think that this could work okay, right? Because they'll step up their power. Maybe that the overall frequency starts falling. But the other generators that are still active, they'll step up their power to account for their guys. Things can work out okay. And it can work out okay sometimes. But what sometimes happens is something like this. So outage happened here at generators 1 and 4. It actually was in this case. And very quickly, bad things start happening. So what happens here is that the system goes unstable. The other generators are still trying to account for what they see, but just what they see, right? They just look at their own frequency. They say, okay, I'm above or behind. You start getting oscillations. The other generators start having this problem where they, at the frequency at them, I mean, they're not generating any power, but there still is a frequency at those nodes, right? Those start oscillating very, very wildly because they can't control them anymore. And by the time the effects of this spread to other generators, it's sort of too late. They can't adjust fast enough to make these things actually work. And what would happen, sort of, if you look at it from a systems perspective, is that what you would see is that the eigenvalues of this A matrix for this controller here, or A plus BK for this controller here, are now over 1. And so you have some unstable mode, it's called, in this system. And in general, this is not going to go away. It's not like you're going to taper these out. This will actually grow to infinity here. What will really happen for a generator then is at some point you're too far off from where you want to be, and your rotor will break. You're too out of phase with the actual frequency of the grid, and your rotor will just snap in half. You probably don't want that to happen. I mean, that's probably worse than a blackout, right? Because if your rotor breaks, you can't even start ever generating more power again until you get that fixed. So kind of a myopic strategy, that means just sort of everyone's personal best strategy in some sense, would say, okay, look, if I keep going what I'm doing right now, I am going to destroy my generator. I don't want to do that, so I'm going to shut off. So in this scenario, when everyone has these control laws, and everyone acts greedily in this sense, they will all just shut off, and there's a blackout. This is despite the fact that generators 2, 3, and 5, so with these guys out, these two generators are perfectly capable of providing the complete power to the whole system and regulating frequency at every node. And in fact, we've seen a way to do that already, right? LQR is a method that each generator makes a choice based not only on its own frequency, but on the other frequencies as well. You base your action on that. And if you run LQR on this system, the exact same system, generators, so you're doing very well for 100 seconds, generators 1 and 4 go down here. It takes a little while to adjust to this, so you have a little bit. I mean, this is not a big spike as frequency regulation goes. Generators adjust here, and pretty soon you can regulate it again. It's a little noisier now because you're using 3 generators to sort of regulate everything in the whole grid. But this is completely possible for the generators to do, right? The problem is to do this, they have to coordinate. So they can't just say, I'm going to do whatever is best for me and ignore everyone else. They have to actually coordinate and say, OK, I'm going to do what's good for me, but also what's good for the whole grid as a whole. That keeps everyone at the desired amount. And this, I mean, this is sort of a simple contrast here. But this is actually a very important topic in grid security, right? Because what you've seen is that the system is capable of being controlled. But a kind of greedy policy the generators may have will not do it, will not work here. There needs to be communication and joint control of the whole system for this to work. So this is interesting, right? Because I think I've heard this from someone else. Don't quote me on this, but I have heard, and this is sort of maybe a said as a myth, but something like, and maybe it's being meant as an exaggeration, but something like 95% of all blackouts were completely preventable if generators had been able to communicate between each other and had done the right thing as a joint group, rather than just what was best for them. Because when everyone does what's best for them, there's these cascading effects, right? Where someone's going to shut down or think like they're going to shut down, so they shut off. This makes the situation worse for everyone else, so other people have to shut off, more people have to shut off, etc. If it was just that first guy that went off for its own reason, some generator just shut down for some random reason, or maybe a line went down, and everyone just understood how to react immediately and knew the best way to react jointly, there would be no problem. There would not have been an outage. The reason why there are outages or large-scale blackouts is because this does not happen, and there are these cascading effects. So this is a very big topic, as you can imagine, in the smart grid. Things like this will only get worse when you have renewables. The grid just becomes more uncertain. You don't know what's going to happen. I mean, these blackouts in the past have happened with fully dispatchable power, right? What happens when we have 33% wind power? How could we possibly control that? These are all very, very big topics currently in grid security, or kind of old-style grid security, that really the framework of this class has at least given you a first pass at understanding why this is the case, right? Joint control like LQR can work here, but something like PID control can actually fail really badly. Yeah?
So is it just as simple as getting the generators just to switch to an LQR method? Or?
So, I mean, it's not that, nothing's ever that simple, right? Because there's also communication delays. And, right? So this is sort of, if you could control them all instantaneously. These things in real systems are far apart. And even over fairly good networks, a couple milliseconds here actually can be a big issue. And what if you're operating, do you want to operate over a private network or over the public internet? This relates to things like these hyper-physical attacks, because if someone sort of launches a denial of service attack on a generator, they could essentially cut out its ability to get any information from other sources. And so these become very complex issues here. It's certainly not as simple as just use LQR. It's not trivial to use LQR on real systems because there's communication and network constraints involved in that, and delay and lag and these timing things. So And generators might not want to sort of share. I mean, if they're two competitors, maybe they just, I mean, even better for both of them, maybe they just don't want to share data with the other one. They just don't have that capability. They don't want to bother investing in that. So there's lots of issues that come up here, both from the cybersecurity standpoint and from just kind of a control standpoint, that are really sort of fascinating topics that determine whether or not systems like this are going to be able to withstand outages of generators. Yeah?
I have one question. At that part, like 100,
Yeah.
and it get noisy.
Right.
What would happen, like, actual? Is that gonna, like, the light gonna flash?
Oh, right here. Well, so this is actually a very small amount of frequency deviation here. This is 0.05 of one radian per second. So this is actually a really small actual deviation. You wouldn't notice this at all. In fact, the frequency of the thing is oscillating, and this level happens all the time. This is not a big deal. This one would be a big deal. Maybe not even at this point, the end here, but this will just keep going and it will explode. So this is a big deal. But this one you won't even feel.
So, like, the previous one, that's the one most companies are using right now?
A lot of places are doing something very similar to that, yes. And this can cause large instabilities of the grid. You can also tune PI controllers to be better than just that. They could try adjusting differently, tuning their gains to try to, prevent things like this in a better way. They can do that. There are, in the grid though, oscillations that happen like this. And so because of things like this, and because of other things too, there is actual oscillation like this that to a certain extent, actually, in a lot of cases, they just kind of say, okay, we'll just let that happen a little bit and we'll watch it. Right? Because you could actually have an oscillation that it was stable. You could actually also have an oscillation that didn't expand out, but just actually kind of stayed at the same level always. And that's another possibility too. So they're all possible. And sort of what people do is actually oftentimes more similar to the first thing, because you can do it all locally there.
In that case, wouldn't the other generators frequency go out?
They will eventually. It's hard to see here, but they actually do. Like you can see a little bit, the green one is growing. The ones that went off typically diverge a lot faster because they have no control anymore. These ones stay there for a little while, but once things get really far out of phase, it gets really bad. Okay, so we are done for today. And next time we'll talk about those last three things. Maybe I'll even try to go through them quickly so we can have plenty of time just sort of to chat about other potential issues or things like this. Set this up now. I